Welcome back. So we are into chapter number 3, and we have studied the harmonically forced vibration of single degree of freedom system. Today we will understand what is the motivation, why we have studied those, yeah, and is there any application for any course you have. There is some motivation, there is some application. That's why you have as a core course or any course basically. This being a core course, there has to be something very important about this course. Yeah, and today we are going to find out one of the applications of whatever you have studied so far. Okay, so first let us see from where we get some source of like harmonic excitation. Okay, so we have studied the equation mx double dot plus cx dot plus kx equal to f naught sine omega t, like this one. We will start, this is one of the examples, so where we will start from this part, from the forcing part, and then we will see what is the use of this, from where, why actually force is fine, but what is the use of this, from where it comes, where it is useful to have m here and c here and k here. Now what is the relation? So that we are going to see today. Okay, so let's see at the force part, from where the force is coming. So again, this is mechanical engineering, okay, and we are going to actually have a lot of machines. So let us say there are various machines, most of them will have some rotary part which is moving. Yeah, so that we have also studied in theory of machine, for example, right? So finally there is some rotary part which derives, even if it is a 4-bar linkage, so there will be one crank, right? So there will be one which is making the full rotation, or power comes from some motor, and that is, everything is driven by that. Gear, of course, based on rotary motion itself, or cam follower is also rotary mechanism is there somewhere, right? So that really means that some rotary part is actually integral part basically of all the machines. So because of that, there may be some unbalance as well. Okay, so what kind of unbalance we are talking about? So there could be something, let us say, moving. So this is a machine, and where there is some rotor, and because of all the connections, there may be some hinges which is driving something, and like that there may be some unbalance. Okay, so let us say there is an unbalance of, let's say it is a mass m which is rotating about this point, and distance between here to here is E, eccentricity E, and this is the mass m which is unbalanced mass. Unbalanced mass meaning that you can assume for the whole mass, the whole machine, let us say the center of mass is here, and there is one small mass which is rotating about this point O. Yeah, so there is a mass m which is rotating about a point O like this. Okay, because of this rotation of this mass, which has a lever E or eccentricity E, this is going to create some kind of force. Okay, so when this rotates, you know that in order to rotate it, you need a centripetal acceleration. So this is the centripetal force unit. How much? Which will be m omega square r, and direction will be, here r in this case, r is actually the eccentricity e, y the omega is the angular velocity. Okay, so this force you need, this much force you need to derive it with a constant omega. Yeah. Okay, now if you are rotating like this one, then what it feels is a centrifugal force. So centrifugal force, which is also equal to centripetal force, which will equal to m omega square e. Okay. Now let us say one mass attached to a string, and you are rotating like this one. What you will feel is the tension in the string, and this is why, because you need this much centripetal force to rotate it. Okay, so acceleration is inward. Always the acceleration, when you rotate like this one, acceleration is inward, and the value is omega square e. Since acceleration is inward, there will be a inertial force applied to that mass, which will be opposite to the acceleration. It is something like you are in the car, or you are accelerating. Since you are accelerating in one direction, you will feel a push in backward direction. Since you are accelerating in forward direction, you have a force applied in the opposite direction. You will feel a force as if somebody is pulling you behind. Similarly here, since when you are rotating this one, acceleration is towards the center, hence there is a pull outside actually. So this is what the centrifugal force is. So that means actually there will be if this is a string, then there will be a pull in that direction. And what will be the pull? So the pull in this direction will be equal to m omega square e, and this is the force which will be applied this way. Okay. So we know now that there will be a force felt at this point. Okay, so let us say this machine is grounded, means there is some bolt here, okay, bolted to the ground. So there will be forces which is going to be passed on to the ground. Right? There will be if it is not rotating, for example, then if it is not rotating, so in that case, let us say the total mass equal to m, so that includes this unbalanced mass as well. Okay, so total mass is m, then you have a ground reaction force which will equal to mg, right? So this will be, okay, so this is the ground reaction force, r will be equal to mg. Now let us say you start rotating this one, and then here this is also bolted also, right? Then at the ground, what kind of forces are coming? Okay, so forces, you know that apart from this force will also come into picture, right? So this is a static force which is downward. Okay, so this here basically at the interface of that there will be a force, reaction force on this one. If you look at the ground, if it is my ground, so what forces are coming? We have this force. This is ground. So ground is feeling the force equal to mg when it is static. Okay. Now, if it starts rotating now, then since at this time force is this way, when rotor is somewhere here, force will be upwards. If it is here, force will be this way, and so on, depending on where it is, accordingly the force will be. So, if the force is upward, let us say, then because the what do you see here? Since when this is up and force will be upward, then there will be some force applied to the machine upward. Hence, ground will also feel some upward force like this. If this unbalanced mass is here, rotating like this one, the centrifugal force will be this way, and hence the ground also, in that case, ground also will feel some force this way, and there will be some total force apart from this one will be equal to what you have, m omega square r. So whatever force is generated by rotating this is finally passed on to the ground, basically. So what you get? So you do get mg here, and then you have m omega square r, but it all depends on the omega t, basically, right? It depends on at what time you have what I mean to say is it depends on time, basically, right? Omega times t, let us say it has started from here, it gives a theta, depending on what angle this unbalanced mass is making. From there we have to find out what the force, additional force direction will be. The force here will be given by downward mg, that the force, and there is a force created by this rotating mass, and that will also be a reaction force here. Okay. Now let us say we are assuming in only the vertical force only. Okay, vertical force only. So in that case, it will be something like we can say there is a roller here, both the sides. Okay, something like this one, and we just want to know what is the vertical force only. Okay, so this is the bolt, but like this one, and we want to know what is the force, the reaction force here. Okay, so if when the rotor is not rotating, in that case the reaction force will be mg. When it starts rotating, then we assume all the horizontal forces are taken care of by this roller support. Okay, so all the force this side or that side will be balanced by this roller. Only upward force will be taken by these bolts, right? So that means it will have m omega square r will have two components, one is horizontal, so you call it m omega square r cos omega t, and there will be vertical component. So vertical component will be m omega square r sin omega t. Okay, so basically this is capital M G here. Okay, so to the ground. Okay, first look at this one. The machine will have one mg, which is the ground reaction force, and then on top of that we will have the here m omega square r cos this will be upward, so sine omega t, plus or minus we have to see. So basically when it is let us say upward, okay, when omega t, when this lever is upward, right, and it is rotating like this one, right, then what happens? At that time this is going up, I mean the force is upward, so reaction, the gravity is downward and force is upward, so this force is actually working in the opposite to the mg, right? So in that case the force which is being felt here will be less than mg, so value will be mg minus m omega square r sine omega t, right? When omega t is, let us say sine omega t is equal to 1, okay, that is when it is sine is 90 degree, in that case what happens, you feel lower reaction, right? The maximum reaction will be felt when this lever is downward, right? In that case the force will be downward and the gravity is also downward, right? So you have mg plus m omega square r in this case, because sine omega t will be minus 1, so here minus 1 becomes plus, so hence you get this value, okay. So basically what we get is the reaction force, whatever the reaction force you have, same force is going to be passed on to the ground, and hence we can simply say that the reaction or the transmitted force, we call force transmitted, right, Ft, we call it Ft. The force transmitted will be equal to mg minus m omega square r sine omega t, where we are measuring everything with respect to horizontal line, like this one. So variation, if you look at the variation, this is a constant mg and the variation is this one, okay. So actually this excitation part is coming from here, this is the sinusoidal part, right, and this is what is harmonically, this is harmonic force we have been talking about. This is the source of the force we have found out from where this kind of force will come. Once we have that, then next thing will be to actually what to do with this. What we find it here is there will be two components of the force. One is the static force, which is mg, and the other is the dynamic force, like this one, okay. And as we said earlier, dynamic force is the one which is important in vibration. A static load, it will go and just it will have effect on the equilibrium point, okay, the mean position of the mass, right? And that is what the static load will determine. But after that, variation in the force is going to derive it. So this is the variation of the force with respect to time, okay, and this one is the force due to gravity, right? So for example, if you go to a space, for example, where gravity is 0, you can assume, and there what you see is only this part will remain, yeah, and this is going to act, right? So in that case, if actually you will have of the form of f naught sine omega t, you will get exactly the same one, okay. So far what we come to know that there will be some machine which will have some rotor, which will have some mass, a small mass m at a distance e eccentricity from the center of rotation, and this is going to create unbalanced force, yeah, and the value of unbalanced force will be, okay, unbalanced force, okay, will be equal to m omega square epsilon sine omega t. We are talking about the vertical one, right? So vertical unbalanced force in this case. Yeah. So given this one, you know that this is going to have some force which is going to transmit it to the ground, right? So since we are going to attach it to the ground somewhere, if we say engine, there will be some kind of engine mount there. What happens right now is whatever the unbalanced force, every force is passed down to the ground, and this is the source of vibration. So let us say machine there, and there may be some structural member, for example. Let us say there's a beam there, right? And what will it do? This is going to make it vibrate. How? At one point it may have force upward, so it will go upward like this. Then when it rotates, comes down, then force will be downward, so then it will go like this, and so on. That means you increase the angular velocity, you will see the frequency of excitation also increases, and we have seen that there will be somewhere, there may be the resonance, and because of that you have seen that at resonance the displacement is very high, so it is going to vibrate quite a lot, and because of that there will be a problem. The structure can be damaged actually. Yes, there will be material failure. The stresses may increase so much that it may be more than the allowable limit. Yeah. So that's why there has to be something done so that we don't have this kind of situation. This kind of situation means there is no failure. Okay. So that's what we need to do. Okay. So to take care of this, we need to have what we call engine mount, yeah, or we call vibration isolation. Okay. So vibration isolation. Yeah, as in engine mount. And what we do typically, if there is an engine which is creating vibration, that means it has some rotating mass basically, and what we do, there may be some engine mount, something like this one here, yeah, and then we have this structure, whatever structure we have, right, like this one, yeah. So this is the engine mount here, right? And here we have the rotor, let us say. Now what happens? The excitation comes from here, but because of this engine mount, the force transmitted may not be as large as m omega square E sine omega t. It may be lower than that. Okay, we will check basically, is it possible that we have some system here. Now we are going to talk about mass is already there, so not mass. Mass is basically comes from the engine, whether we have a spring and damper there, such that our force is actually less than this one, right? So whatever the force you get here, the amplitude here is m omega square E. If the same force is going to go there on this one, because of the dynamic load, yeah, there may be fatigue, for example, yeah, in the structure, it may fail. So we want to reduce the amplitude of the dynamic force. And for that, we want to use a spring damper here, such a way the force transmitted to this structure or to the ground, okay, is less than what the force is. So that's what we want to do. So let's start with, we will now just write it as M. This is the big M. Okay, so big M means it is mass of the engine and mass of the rotor as well, all combined. That's the M. Yeah, and then we want to design some engine mount. Yeah, so, and here is the ground. So this is the ground. Here it is K, we have C here. We have to choose K and C such a way that the force which is going to be transmitted, which is less than whatever is a desirable value. Yeah. So M will have some kind of force, we can say now here, F, where F equal to F naught sine omega t. Okay. Now we are leaving aside the static load. Say, so when I was explaining that, we started with the static load mg, but a static load is not a problem. Okay, so we can, if it is the load is just sitting there, no problem. The problem is when the force is dynamic. In that case, it will create noise. That's one thing. The vibration will travel basically through the structure, and also the structure may fail easily at lower amplitude. Also, with the dynamic load, the structure can fail as compared to the large force in case of a static load. So that's why the dynamic load is actually dangerous. So the static load we are keeping aside. Yeah. So even if we consider the gravity, you know that in this case, this is going to go down until the spring displacement is going to balance the force, and that will be the mean position and it is going to vibrate like about that mean position if you get it, if you give it dynamic load like this one. So that we know already, so no need to actually repeat it here. So given this one, force is applied here F as we have done earlier. This is no different. Exactly same system. Earlier it was like this, right? And like this, F equal to F naught sine omega t. Here it is just upward like this one. Why? Here we are drawing such a way, this is like more practical, right? When you have an engine here, let me write it is here. So you have some engine here, and this one, the whole thing, yeah, so including K and C both, is engine mount, right? For what? Engine mount for vibration isolation. Vibration isolation. Okay. Okay. Now we have solved, both are same, right? There is no different. We have solved already. So if F is like this one, we know that X, the displacement, is given by X equal to X naught sine omega t minus phi. That we know already. Okay, we have done yesterday also. What we want to know here is what is the force transmitted to the ground, because that is the important, right? So if the force transmitted to the ground is small, then our engine mount is good. Yeah, and in order to know that, we just first see the graphically. Okay, so yesterday we actually drew this one, this real number imaginary axis, And what did we do? We drew this which is kx. Then we had cx dot, and then we had my m mx double dot here, yeah, and then this was the force F, right? Okay, from here to here was phi, here to here was omega t, and hence here to here omega t minus phi. So this is the picture. So instead of minus, let's call it mx dot double dot. So this is how in the vector plane all the forces look like. If I ask you what is the force transmitted to the ground, what will your answer be? Just look at this figure and tell. You know that here, whatever the force, the mass feels here, where the spring and damper is attached, the same force ground will also feel. What it feels is force because of spring and force because of the damper. So basically, which force? This force. If we say Ft is the force transmitted to the ground, Ft will be this dashed line. The force due to the spring, then force due to the damper, and then you join it, and this Ft from this end to this end will represent the force transmitted to the ground. So a good engine mount or vibration isolation device will be the one which has this Ft smaller than this F. Yeah, so right now you see it's not. What you see right now is just although just in graph only, so you see Ft looks bigger than this F. So it's not a good design actually. Actually this is in fact worse than just putting this, bolting it to the just structure. In this case, what you see, the magnitude is even more than this one. It's a magnifying basically the amplitude. But we can do something about it, right? And that's what we will learn something on that. Okay. So in order to find out how good this vibration isolation devices or the engine mount is, we have to find out the ratio. Okay, what ratio? The ratio of the transmitted force Ft, let's call it TR, because this is actually known as transmissibility. So transmissibility, TR. Okay, this is a ratio. And what is the ratio? Ratio is Ft over F naught, where Ft is the where Ft basically, let's use like this. Okay, so magnitude of the transmitted force divided by F naught. F naught is the magnitude of the excitation force. Okay, so we have to find out this one. Yeah. Okay, or we call it let's call it Ft0 divided by F naught, where Ft0 is the magnitude of the transmitted force. Transmitted force comes from here. So transmitted force TF ft will be given by, we have in terms of the vector notation also we can use, right? So we have a will be fx. So we know that we will have kx, and then plus we have cx dot. But in vector notation, actually this like when we say kx plus cx dot, this is, here it is implies that x and x dot both are in complex. So what we are talking about, x dot in complex. Yeah. So what we get is k x naught, and then we have in this case sine or x naught ei omega t, okay, and minus phi that we know, plus here we have c x naught e I omega e to the power I omega t minus phi. So like this. Okay. So what do we have? We have x naught, and then we have k plus I c omega, and then we have e I omega t minus phi. Okay, this is what we have. So that really means that ft0, which is the magnitude of this transmitted force, will be equal to ft, and what do we get? We get x naught, and here we get root k square plus c square omega square. That's what we get, ft0. Yep. So we have this ft0, x naught times root k square plus c square omega square, and transmissibility tr, we define it as ft0 over f0. So that means we have x0 root k square plus c square omega square divided by, we have f naught, or is equal to x naught over f naught, okay, and then root k square plus c square omega square. Okay. Okay. What we need now is the value of x naught. Okay, so how to find out x naught? Either you can remember or you can just work out quickly. So what the equation we have? We have in this we write capital M because that's what we denoted the whole machine actually. So mx double dot plus cx dot plus kx equal to f naught ei omega t, and we assumed the x equal to capital X naught, okay, e I omega t minus phi, that you put it here. So finally put it here, then what do you get? You get minus m omega square, okay, then here you get I c omega, here you get plus k multiplied by you get x naught e I omega t minus phi is equal to so equal to f naught e I omega t, and hence what did you get? You are getting x naught is equal to f naught divided by simply minus m omega square, rather k minus m omega square plus I c omega. Yeah, so from this equation you will simply you get x naught if you take the magnitude both the sides, so what you get is x naught equal to f naught divided by the magnitude of this, so k minus m omega square plus I c omega, right? So this is what you get. Okay, so x naught we have, or simply we can write it as f naught, or from x naught over f naught. Okay, so x naught over f naught is equal to 1 over, and x naught over f naught you get root under k minus m omega square plus c square omega square. That's what you get. Yeah. Okay, so TR, this is transmissibility. In that case, you get TR is equal to x naught over f naught. So this value and over there. So what you get? You get k square plus c square omega square divided by root k minus m omega square plus c square omega square. So this is the transmissibility. Looks like in terms of k, c, m and omega. Okay, we can also convert that into omega n and zeta term as well. Okay, so let's now write in terms of omega n and zeta also. So we can write this k, we can take this out. So what we get is root 1 plus c square omega square omega square over k square omega square divided by, okay, and here we get similarly root 1 minus m k square plus c square omega square over k square. Okay, also we know that m over k is omega n square. Okay, so we know we have already given these relations earlier. So this is one. Second thing is zeta is given by c over 2 root km. Okay, so c over k really means you multiply root k here and root k here, like this one. So what do you get? You get equal to zeta. That means zeta equal to c over 2, then this comes k, and then k over m. So this is what the zeta will be, and that is equal to c over 2k multiplied by k over, okay, sorry, here it will be m over k is here we have also left this one, so omega square will be here. M over k is 1 over omega n square, so this is 1 over omega n square. K k over m, this is a big M, sorry, so whatever, okay, so this is a big M, okay. So C over 2k, k over m is omega n actually. So what do you get from here? You get actually C over k. C over k is equal to 2 zeta over omega n, and hence C square over k square equal to 4 zeta square over omega n square. Okay, so we can put that there and we can get the transmissibility value finally, and the value will be Tr is equal to root under 1 plus C square over k square is 4 zeta square omega n square. So 4 zeta square omega over omega n square divided by, we have this term, and here we have 1 minus omega square over omega n square, then square plus we have C square over k square, so CO square over k square, so C square over k square equal to 4 zeta square multiplied by omega over omega n square. So this is what you get the final value. So this is finally we get this expression for the transmissibility. Okay, and if undamped condition, so if we don't use any damper, if we don't use any damper, and in that case zeta will be equal to 0, and in that case Tr will be equal to zeta, you can make it equal to 0, and you get 1 over 1 minus omega square over omega n square. And you can see here that when omega equal to omega n, then transmissibility will be very high. Yeah? Hence you design a system such that if you are, let us say if you have just using the spring, then you are going to design a system, the engine in such a way omega n will be not be matching with the omega of the unbalanced, the rotation of the unbalanced mass. So you should not match it. If you match it, then there will be very high transmissibility, the transmission of force to the ground. Okay. Now looking at this equation, you can also see what will be the desirable parameters for a good engine mount, right? So one thing is not to match the frequency of the excitation force with the omega n of the system. That will be one thing. Second thing, what we see is, see here, it is 4 zeta square omega over omega n square. This term is also here also. So this term is very crucial. That really means if we somehow increase this one as large as possible, then we will get Tr as small as possible. And what is the meaning of that? That will only happen when we have like omega n as small as possible. Yeah? So if you have omega n very, very small, then what happens? omega over omega n will be a large value. We are looking for possibly much more than 1, and hence 1 minus a big number here, which will be a squared, and that is the term which appears here, and hence denominator will be larger than the numerator, and hence this TR value will be less than 1. So desirable, one ideal engine mount omega n is very, very less than omega. Yeah? And this you can see in this case, in case of the like undamped oscillation as well. So undamped case as well, you get 1 over 1 minus omega square divided by omega n square. And in this case, if you have omega n very, very small, then you get 1 minus here value which is much more than 1, and hence you get 1 over a large value. Yeah, so hence you get TR, which will be negative. The meaning of negative is basically when the force is going upward, then the transmitted force will be downward. That's what is the meaning. Okay. So in both the case, what we see is the ideal engine mount will be when the omega n is as small as possible in comparison with the operating omega, the angular speed of the rotor. Yeah. So we know that omega n is equal to root k over m, and that tells it if we want omega n to be a small, okay, choose a small k, right? A small k. Okay. A small k means what? Less stiffness, and hence we use some soft material, choose a small k, or that means soft material basically. Yeah. And that really means, for example, rubber, right? So rubber, that's why it's used, because of one thing it has some damper, so that it is not undamped condition, because you know in undamped condition the vibration is much more. Hence rubber has some damping property, and hence rubber is a good choice. Plus it is a soft material, and because of softness it results into less stiffness k, and k divided by m, root of k divided by m is omega n, which also is a small. Since this is a small, because of that, if you put this here, what you get is transmissibility is low transmissibility, and hence you have this material in use.